Thanks to you all for coming. So with fall break being next Monday, obviously there'll be no class on Monday. I will, however, hold my office hours that afternoon in Alderman Library. So those of you who are hanging around for the reading days instead of the, anyway, I can joke about the name reading days. I'll be in Alderman Cafe that afternoon. Wednesday, there's no class. I'm canceling it entirely, including my office hours. So the problem set, next problem set is due on Friday, and my office hours will be on Friday instead of Wednesday. So in my office, 9 to 11. Any logistical questions, class stuff? Do remember to use this, send me messages. In fact, there's one here that I'll respond to it before going any further. But it was good when it was working, when you all were doing it. Okay, so back to material then. The question here is going back to the loop-the-loop story. And where I was showing you that if you reach out and push on a ball as it goes by, sure, you can push on it. And it will, consequently, it will accelerate under the influence not only of its weight, but of your hand pushing down. And so the net force on it's greater than its weight. It's accelerating downward faster than its weight. And the question asks, what happens after you stop pushing? And the moment you stop pushing, and the ball is still above the ground, it returns to accelerating downward at the acceleration due to gravity. So it's back to falling. But you've given it this huge, actually an impulse, you've given it extra, boosted its velocity enormously. So in that brief pushdown period, you cause it to speed up faster. And then it goes back to normal speed up. So the roller coaster, a loop-the-loop, it has to keep pushing you down the whole time you're inverted. Otherwise, you'll just be falling. And you'll feel weightless, which is not really supposed to be part of the loop-the-loop. And you may start to lift out of your seat. You're no longer pressed into your seat. So also a bad thing, unless they've got you strapped down. Okay? Well, where I left off was a little farther along, and that was with bicycles. And I talked at sort of the end of the class about how the bicycle steers itself under you so that it steers, in fact, under you what? Under your center of gravity, so that it returns you to an unstable equilibrium. So now I've got a broom back. And so a broom by itself, clearly it's got a rounded tip. It has an unstable equilibrium, but it will never stay there for any length of time. I mean, you can never get it in there. And the slightest disturbance will cause it to go over, because in an unstable equilibrium, it's at a maximum of total potential energy. This is as high as the system can get in altitude, therefore as much gravitational potential energy as it can have without lifting it off the table. So it's sitting there in the highest possible total potential energy, that being gravitational, and any tip lowers that gravitational potential energy. Hey, it loves this. It accelerates in the direction that lowers its total potential energy as quickly as it can, down it goes. So that's a disaster by itself, but you can fix it by perpetually putting your hand under the center of gravity. And I'm guessing the center of gravity is right around here. So that's where I'm looking. Again, I'm not looking at my hand. That's hopeless, okay? You got to look at the center of gravity and go under it, okay? So the bicycle does it automatically for two interesting reasons I showed you. One is that if you tip the bicycle, it pivots the steering axis to lower its center of gravity, to get rid of potential energy. So it does this automatically. It is, incidentally, possible to design a bicycle that does the reverse, that when you tip it, it steers the wrong way. It's hard to do. You got to really, it won't look so much like a bicycle anymore. And it's unrideable. And a fellow in England in the 60s built such a bicycle and discovered, sure enough, it's unrideable. You need that automatic steering. Without it, in fact, with automatic steering the wrong way, it's just not doable. The other effect was a more exotic one, and I did it in a flurry. I spun up the wheel and hung it from the ceiling, and you see that the wheel pivots. And let me just walk you through it without spinning it, just to walk you through it so you see why this happens. It's one of the fascinating pieces of the world of angular momentum. It's probably too tough for you to remember for any length of time, but you ought to see it at least once. And the idea is this, that if the bicycle is heading away from us, we're riding the bicycle, okay, we're all going that way, the wheel will be spinning this way. That's the necessary direction of rotation for it to roll. So if it's spinning that way, that's angular momentum to the left, according to the right-hand rule. This is why did I introduce the right-hand rule? It's for this sort of purpose. So you can see, my thumb's pointing to the left. If we start to lean the bicycle like this, you would think it's going to fall over. But what happens then is the ground pushes up on the bottom of the wheel. Instead of pushing up straight towards the center of rotation, which it did when it was upright, it's missing. It's pushing up in this direction. It's missing the center of rotation. And that means it's pushing at an angle. It's producing a torque on the wheel toward you. It's trying to twist the wheel so it rotates this way. In fact, if I just let go of the wheel, of course, it does rotate that way. Then there goes angular acceleration, over it goes. So the wheel has angular momentum to the left, but when it tips, it starts to be given angular momentum toward you. That means the angular momentum of the wheel pivots from leftward to toward you. The wheel does this, it pivots as its angular momentum evolves from being leftward to being toward you-ward. And that steering of the wheel is the right steering to save you, to drive it underneath you. So that effect, it's called precession. There are gyroscope toys around that exhibit that beautifully. They used to be familiar parlor toys, but in the modern era, there's just an app for it or something. It's kind of lost. Anyhow, automatic steering is a key feature of bicycle riding. Keeps you upright and so on. All right, one last thing to talk about, and that is, so why did you even go to a bicycle? Why not ride a tricycle? Remember, tricycles have this nasty inertia problem, that if you're going very fast, you make a sudden turn, the vehicle drives out from under you, and your body goes straight and inertially, and the vehicle's gone and you crash. A bicycle has, you're giving something up. You're giving up static stability when you go to a bicycle. It's no longer something you can balance easily while you're at rest. You have to be moving to use the automatic steering. But what you can do when you're on a bicycle is you can lean. You can tip the bicycle deliberately. And you do during turns. And so here's the idea. When you are turning a bicycle, you're balancing two separate effects off against each other. And here are the two effects. So I didn't bring a bicycle this time. I'm just going to use another thing that's in an unstable equilibrium, which is the broom. And we're going to be heading away from you all, okay? We're going to go this way. If I turn without leaning the broom, so I'm going to walk forward and then I'm going to turn. Watch what happens to the broom. So we go forward. It goes inertial. It tips over actually to the outside of the turn. So I was going around like this, or trying to if I pay attention, and it went inertial, and the top, which you went flying toward the outside, okay, of the turn. So that's one thing. If you turn without leaning, you crash to the outside. That's the idea. Now, what if you lean without turning? So now let's let you lean to the left and no turn. You crash to the inside. So these effects are opposite one another. Turn without leaning and you flip over inertially to the outside of the turn. If you lean without turning, you flip over because of gravitational effects, torques, to the inside. What if you do both at once? And that's the key. When you turn your bicycle, you lean. God, this is hard to do. I've tried it before class. You can do it in principle. So you lean it and turn it. You can keep it upright. You're balancing those two effects off against each other. Is that okay? And you do this not only on a bicycle, you do it any time you turn something that can tip, including yourself. If you're just running a track race around the turn, so you got a race that's long enough that it doesn't run on a straightaway. when you go around that turn, you can't just run upright. If you do, you'll do what the straight up, you'll do what the broom did. When you turn without leaning, you'll flip over to the outside of the turn. So in high-speed races, you're always leaning toward the inside. You're balancing those two effects off against each other. Is that okay? And that's the beauty of the bicycle, is once you get moving, it's stable, because it's self-correcting, and during turns, you can lean it and cause it to balance these two effects off against each other. You can basically turn a bicycle or a motorcycle as hard as you like. You just have to lean more and more and more. And if you've seen bicycle races, certainly they're leaning hard during turns. In motorcycle races, they're leaning so hard that they have to worry about like sanding their legs on the ground. They're almost horizontal. The limit finally is how hard the wheel has to grip the ground well enough. It has to have enough traction that it can complete the turn without skidding, and that's probably the biggest limit. But anyway, you can lean as hard as you like if you're accelerating around that turn fast enough. Is that okay? Any questions about this idea of leaning during turns? Watch yourself doing it if you're riding a bicycle or if you're running around a corner. All right. So that's the story of bicycles. I think I'll leave the machinery of the gears and all that for some other year. And move on to another topic, which is rockets. All right? So rockets, let me start off with I'll ask you one of these questions on the clicker. Go back. He immediately presses the wrong button. All right. And the question is this. It used to be standard business to watch these big space-bound rockets take off, and you interrupt school to watch them go up. And now they're kind of dime a dozen, I guess. And I don't know whether you've watched one happen anymore. When they take off, they're typically on some launch platform, and the flame shoots out the bottom, and it's all over the launch platform, and up the thing goes. The question is, if there were no launch platform underneath the rocket, so it was still vertical and all at launch, but there was just nothing underneath it, the upward thrust, the upward force acting on the engines would be, same, different. Any questions about the question? See what you think. All right, give you another 10 seconds or so. 5, 4, 3, 2, 1, 0. Ooh, it's pretty all over the map. Majority going for 0, which is good. Okay, interesting observations to see. So, you want to know the answer? It's going to be A. The launch pad doesn't matter. The launch pad is a nothing in the story. And you might, so actually this gets to the point of like, okay, so how does a rocket work? And for those of you who didn't choose A, you're in good company for just thinking that. I think it's still in the book. I don't know where it's gone these days. There was an editorial in the 20s, I think, from the New York Times, upbraiding Robert Goddard, who was making liquid-fueled rockets and stuff, and planning to go off into space. And here's this editorial by these, okay, it's New York Times, think of what you like, saying, what an idiot, basically. Goddard's going to plans to send rockets off into space. He doesn't know what any high school student knows, that action-reaction, you have to have something to react off of. So if you're in space, there's nothing to push on, you can't make a rocket. It's going to do nothing up there. So clearly, rockets were mysterious. The editors at the Times were simply wrong. They didn't understand how rockets work. So here's how rockets work. And finally, the story is very simple. Rockets work by pushing on something. but it's not something outside the rocket. It's something within the rocket. They take stuff they have, typically fuel, and push it in one direction. And if you do that, the stuff you pushed in one direction pushes back. That's Newton's third law, right? If you push on junk to the left, it will push you to the right. And that's how a rocket works. It takes stuff it has on board. And so, for fun and games, you could have a rocket that just it's just a vehicle. If you were in deep space and didn't have to worry about gravity and everything was simple and you could just do it, you could just have a rocket that was just, I don't know, your cluttered camping trailer, all the stuff. It's just in there in space doing nothing, sitting still. You can start taking the stuff and throw it all that way. And every time you do that, it will push back on you. Because to make it accelerate that way, you've got to exert a force on it. It will exert a force back on you, and you'll slowly pick up speed. So here's me in my trailer, and right now we're motionless. And incidentally, we can look at this in terms of forces and accelerations. We can simultaneously look at it in terms of momentum. Right now, my momentum, me and the whole camping trailer, what's the momentum of the trailer? 0. And if we're in deep space, isolated from everything else, it's always going to be 0, because we're not going to exchange momentum with anything else in the universe, just us. But that doesn't mean that we can't rearrange it locally. So I only have one thing in my trailer. It's a medicine ball. And right now, the two of us individually have momentum 0, along with having total momentum 0. But if I give this guy momentum left, I'm flying, whoo, off I go, right? I gave it leftward momentum. It gave me rightward momentum. Our total stayed at 0. I'm still going, how about that? As I say, do not stand. One of these days I'm going to get nailed. We started with 0 momentum. We ended with 0 momentum. But it was now distributed funny. That guy had 6 units to the left. I had 6 units to the right. Sum total, 0. Is that okay? Furthermore, looked at it from a force point of view, I exerted a leftward force on it for a period of time. It exerted a rightward force on me for a period of time. Off we went. Our specific accelerations had to do with our masses. It's got less mass than I do, so it accelerated a lot more than I accelerated. But it all works out. And that's it. Rockets are done. The only thing left really is, how do you make a better rocket? I mean, that obviously is pretty crummy. So it's the details. And to do better, we look at what you're trying to do. You're trying to give the stuff you throw out that direction as much momentum as you possibly can. And you also want to throw as much stuff out there. First of all, you want to have lots of mass to throw that way, because the more mass you have to throw that way, the more momentum it carries away. You also want to go very fast, because the faster it's going, the larger its velocity, again, the more momentum it's carrying away. Because the momentum of anything is its mass times its velocity. So if you want to have a lot of momentum in yourself, in whatever the spaceship is, going to the right, you want to give as gobs of momentum to the stuff going to the left. So you need a lot of mass, a lot of speed. Me throwing the medicine ball, it's something like a tenth of my mass, and I can throw it at 2 or 3 meters per second or something like that. Not very good. Can we do better? Yes, we can do better. And let me get this out of the way just because I can. All right. For this now, get me out of the story, we need a rocket pilot. Volunteer, one of you guys, who wants to ride the rocket cart? Somebody? It's boring when I do it. Please, come on down. Yay. There's one good trip and one less good trip in this canister, so I'll get a second one of you guys. You remind me your name? Connor. Okay. You actually, it's loud, so you can wear these guys. But the other thing, the helmet's just for fun. You can wear it or not if you want to.
We'll see how it goes.
Okay. What you do here, that's the safety. Have a seat, face that direction. with nothing touching the ground. So pull your feet up. And this is all set, right? Yeah, reach behind you and squeeze the two handles together. And when you do that, there'll be a loud roar. It's up higher. The handles are up high. You can position yourself so you can get the job done, okay? And you squeeze them together and stop. By the time you get about here, you'll be going fast enough that you want to stop, okay? All right. Yay! Thank you. Thanks, Connor. Return trip. Someone want to take it for the return trip? Come on. All right. Coming up. Bashir is going to do it for the return trip. Again, So this is actually not a normal CO2 fire extinguisher. It's been modified. The normal ones spray the gas in many directions for good reason to not have this effect occur. Yeah. Okay. And you probably can use the whole thing to blast across the room. Okay? Squeeze hard. Yeah, it's the last portion of CO2 is never quite as satisfying, but thank you. Yay. All right. So the point is, that was not very much CO2. It was a few pounds, much less than that medicine ball, but it's coming out at several hundred miles an hour. And that makes all the difference. So to make an efficient rocket, stop, get it out of the way. To make an efficient, effective rocket, you want that exhaust, talk about it as an exhaust velocity. Yeah, the direction is backward, but you want the speed part as big as possible. And so how do you get really big speeds in the exhaust material? You typically use things that have lots of energy in them because along with carrying away momentum in one direction, the material is moving fast and has a lot of kinetic energy. So to get very high speeds, you need a lot of energy to give it as kinetic energy. So rockets, this is why rockets use fuel that burns. They release vast amounts of chemical potential energy. So that the particles involved, which are gas particles, and we'll come to it very soon in the course, the gas particles are moving really fast because they're so hot. They've got a lot of thermal energy. And then the rocket engine then works very carefully and strategically to turn that thermal energy as best it can into one-way kinetic energy, carrying the gas out at high speed. And the act of getting that gas moving so fast involves forces and momentum transfers, and the remaining ship ends up with the opposite force and the opposite momentum. And next on the list of things to do is probably this rocket. Well, I'll do water rockets first because I can do them. They're fun. All right. So if you really cheap rockets. This rocket has a lot of mass to work with. Most of the mass of this rocket is water. So it's been filled up to there. And so it's got the mass to throw it backwards, but it needs an energy source to get that water moving fast. And the energy source is going to be compressed air. So I've got a little pump here. And my job then is to do work. Force, distance, right? Force. And I think it says, do 3 pumps, and I do 10 pumps or 15 pumps, or until it starts leaking on me. Okay. Oh, or stab me in the hand. There we go. Oh, it's leaking. Misfire. They scrubbed it at the Cape. All right, try again. I'm not like SpaceX where I can land it back down on the, woo, up it goes, all right? So thank you. Just the right kind of stuff for right before break, right? So it had a lot of mass to work with, it had a lot of energy to work with. Not a lot on the grand scheme of things, but good enough, and the result was that it managed to propel itself pretty effectively. Okay, this one, and now I'll need a launch pilot. This one's hairspray powered. Someone want to launch this one? Please, come on down. Yeah. Years ago, we had this arranged low, and you could stand behind it when you launched it, and the bottle cap came flying off and hit one of the divers from the swim team. This will not happen to you, don't worry. I'm just telling you, I'm telling you the story. We haven't buried too many students in this class.
Cool.
Run me your name?
Raina.
Raina. So Raina is going to launch this. And here's the idea. I'm going to put in 1 dose of hairspray in this bottle. It has a small hole in the cap. That should probably be enough. Got to let it evaporate. And these guys, how does this one works? It's different. Okay, yeah. You just squeeze it. You just hold that right behind the back. It'll go whoosh. You squeeze the whole handle. There you go. Okay, just hold it behind the nozzle.
Wait, like here?
Right?
Oh! Can I do that again?
Can you do that again? Sure. More is better. We have to get out out with the bad air, in with the good. Here. You blow out the burn gas. Now you know what to expect. The only trick with this is not putting in too much hairspray. There's a right amount. Too much is. We don't have to alert like the FAA or anything like this. It's pretty safe. All right, ready? We'll put in some more. Oh, stop dancing. Okay, we gotta let it evaporate. Another 3 seconds, 5 seconds. Okay, about now.
Okay.
Go for it.
Okay. Nope. Yeah. No.
You've knocked off the stop.
Every time that just gives me a heart attack.
All right, thank you. Yay! You can try it again after class. So anybody who wants to come up here and be rocket pilot, yeah. All right. So the idea again is lots of energy released by way of burning the gas, the fuels. So this is why essentially all rockets are fuel-based. They burn a fuel. They can't count on the passing air for the oxygen. They have to have it on board. So they're burning chemicals they have locally within their system. And the highest energy they can come by really is liquid hydrogen and liquid oxygen. So it's about as dense as they can get for energy. They can go to hydrogen and fluorine, but that's a little more energy, but it's nasty. So they're burning the highest energy fuels they can have. Yeah, Bashir?
The airplanes, the same boat air, they take in air and push it back.
Yeah, so Bashir's observation is that airplanes are a little different. They take in air and push it back. Airplanes, so jet engines in particular, are not that different from rockets, except they're air breathing. So they instead of having the air on board, they have only the fuel on board. And they bring in air, mix it with fuel, and they do the same effect. They throw it backwards. And they do it very effectively and get a lot of propulsion out of it. Obviously, it's more weight efficient because you're using something that's locally available, air. Rockets, not so much. They have to carry it. Okay? And there are lots of different fuels for different purposes. But a point is they try to go as fast as possible with the fuel. So all very high energy things, which is why if there's a problem, it's a big problem. Stuff burns up just terribly. That brings us to another question I'll ask you about, and that is this one. What's the speed limit for a rocket? You see the idea that you can throw it backward, the fuel backward, and it will push you forward, and that's all good. How fast can the rocket go? You okay with the question? See what you think. And the words I'm using, the rocket is the whole assembly at launch time, and the spaceship is the piece that you care about, that you're flying in, for example, not the fuel. All right. 5, 4, 3, 2, 1. All over. E was the right choice. No, it's actually D. There's no limit. There's no limit. And to give you an idea of, but it's not obvious. So don't feel badly if you didn't choose it. It's not obvious because it sure seems like that's the fastest thing in the whole story. How can you possibly go faster than that? Than that rocket fuel exhaust? Well, as a way to think about it, suppose you have 5 rockets all stacked on top of each other, one on top, a really big rocket, and sitting on top of it is a big rocket, and sitting on top of it is a medium rocket, and sitting on top of that is a moderately small rocket, and then on top of that is a tiny rocket. Burn the big rocket first. Off it goes, and suppose it can go close to the velocity of the fuel. Stop and light the second rocket and let it go. It's still doing the rocket trick. It's still throwing fuel backwards, so it goes faster. So it speeds up, so it goes faster than the big rocket. And you do it one after the next. Sort of a Russian doll type rocket. And actually, that is how some of the early rockets were built. And to an extent, they're all built that way. They're staged. That is, they start with a biggest rocket, and they work their way down to smaller and smaller rockets. It's a little more subtle, the transition from bigger to smaller. They start throwing away pieces. And the idea, finally, is this, that as long as the final spaceship has a tiny mass compared to what launched, you can keep giving backward momentum to lots and lots of fuel. It's got a big mass, and if it managed to go at the exhaust velocity, that big mass traveling at that exhaust velocity carries an awful lot of momentum backward. And if all that opposite momentum is invested in one tiny little ship with very little mass, it has to go very fast to carry that much momentum. So it easily goes past the speed of the exhaust. And the extent to which you can go faster than the speed of the exhaust is dependent on the ratio of fuel that's going to go backwards and ship that's going to go forward. So if they're 1 to 1, if there is the same amount of fuel as ship, it's not going to go faster than the exhaust velocity. But if it's 10 to 1, if there's 10 times as much fuel as there is ship, you could imagine situations in which the ship is going 10 times as fast forward as the fuel is going backward. And you can keep on going. In reality, you can't get that extreme in the forward speed of the ship. This comes about because the ship is throwing away fuel as it's accelerating. And so some of the fuel that's thrown late in the story was actually accelerated forward and wasted some of that precious forward momentum. Not only is it not important to be going forward in the future for that fuel, but you invested forward momentum into it, and now you throw it out. And so you can't go, it's hard to go many times faster than the fuel velocity, but you can go several times faster than fuel velocity fairly easily. And that turns out to be crucial for space launches, for people getting off the Earth in rockets. The rockets managed to get pretty amazing exhaust velocities on the order of 3 to 5 kilometers per second. So that's how many miles an hour? It's like 2,000 miles an hour, that kind of thing. The exhaust velocity is really fast. But even so, they have to get to speeds more like 15 to 20,000 miles per hour. They have to go several times the exhaust velocity. We'll come to why they have to go that fast in a second, or in a minute. But they need that extra speed. And as a result, they need to be throwing an awful lot of fuel downward in order to propel a small vehicle upward. This is why the rockets at launch are huge, and what actually gets to space is dinky. You can't do better than that. There have been efforts going on for 20 years or so to try to get a ship, a single ship that is that much fuel. It's 90% fuel at launch, and that therefore the whole thing can go to space without success. So all these wonderful movie, science fiction movie, Millennium Falcons and stuff, where they hop in and they take off and they go to space. You can't do it because you need to blast so much fuel backwards that the thing's got to be 90+% fuel at launch. So, shrink the crew compartment, it's all fuel. And how do you make a bottle that holds this incredibly high energy fuel, this stuff that burns like nightmarishly? How do you hold it when you're holding 90% of the mass is the fuel and the bottle? What's the bottle like? So anyway, it's a problem. So alas, a lot of science fiction movies are science fiction. But we can do it with these stage systems where you're discarding parts so that you manage to have lots of big fuel bottles and you kind of winnow them out of the system and you get smaller and smaller parts going into space, and they do get to space. And are we okay with the rocket stuff so far? How you get it going? What do you do with it when you get to space? Well, if you go straight up with a rocket, and you might get to 200 miles above the ground and stuff like that before you kind of run out of fuel and you're starting to coast and maybe gravity's still pulling backward on you because 200 miles is not that far, much farther from the center of the Earth than we are now. So the rocket parts that are up there are still weigh a lot, and they slow to a stop and then they come back down. And a lot of the early space launches were like that. Basically straight up, they go up as high as the rocket will manage to carry them, they run out of fuel, they run out finally of kinetic energy, and then they fall back down to Earth. And the early versions of commercial space trips I guess they're sort of starting to happen now. They're straight up, straight down operations. So you go up to peak height and then come right back down. But most of the interesting space stuff goes into orbit. It's not straight up and straight down. Stuff goes up and it doesn't come down. And why not? Does gravity go away? And the answer is no. It does fall off as it gets weaker with distance from the center of the Earth. It's a subtle effect. It's worth pointing out. I've talked about gravity being constant down here at the surface of the Earth. My weight here is the same as my weight here. It's not quite true. My weight right now, it's a little smaller than it was down here because I'm a little farther from the center of the Earth. And it turns out that the force of gravity is proportional to 1 over the square of the distance from the center of the Earth in this case. So I made it a little farther away, I'm a little lighter, just a tiny bit. But by the time you get hundreds, thousands, tens of thousands of miles away from the Earth, that effect is getting important. You're starting to lose, gravity's getting weaker. The weight is really going down. But most of the manned space, that is, all the manned space, or people, I should say human space, people up there, with the exception of the Apollo trips, which left the Earth behind, the astronauts up there, they're all so close to the Earth, 100 miles, 200 miles, 300 miles, that they basically have their full weights. And so the ship, same thing, full weight. And so if there were nothing else going on, it would fall. It is falling, actually. They're falling objects up there. Engines are done, fuel's gone, they're falling. But they don't hit the Earth. And why not? Because they're going sideways so fast, that is horizontally. They're traveling horizontally at tens of thousands of miles an hour, really fast. And the result is bizarre. They keep falling toward the Earth. That is, they're accelerating toward the center of the Earth, but they're making no progress toward it because they're going sideways so fast that the Earth is curving out from under them as they fall. So this is the Earth. Here's the astronaut there. They're going sideways. I can't do the whole Earth at once. I'll walk with you. Here's the Earth. The astronaut's falling, but the Earth is curving away. They're making no progress in altitude. They maintain, for example, a constant altitude, 100 miles all day. And there's a specific speed they have to be traveling for that effect to work. If they're going too fast sideways, inertia wins and they go to higher and higher altitude. They basically leave the Earth behind. They just fly off straight. If they go too slow, gravity wins and they arc down, get lower, lower altitude and hit. So they have to make a right balance. So they pick a specific speed. So for any given altitude above the Earth, there is a correct speed. And for these low Earth orbits, which is what most peopled space situations are, that speed is about 17,000 miles per hour, give or take 1,000 miles an hour. If they go slower, they come down. If they go faster, they go out. Going out is not so bad. It makes the orbit funny shaped. It's still an orbit. It still closes on itself, which is an amazing thing. It goes out, it gets too far from the Earth because it was going too fast. It slows down as it loses kinetic energy for gravitational because it's getting farther away from the Earth, and it works its way back in, and it comes back to where it was and loops again. The closure of these orbits, that is, they keep going by. You can sit there and watch the thing go by once, and about 90 minutes later, it's going to be going by again. That's about how long it takes one of these low Earth orbit spacecraft to go around at 17,000 miles per hour. It's about 90 minutes. So that's why all the satellites down here do the loop every 90 minutes. Philip? How about geostationary satellites? If that 90 minutes, if a ship were going 17,000 miles an hour toward the east, due east, over the equator, it would complete the loop in 90 minutes. And the Earth would have turned, it would have turned about 1/15th of full rotation. Not enough. So the Earth is trying, instead of the Earth, the equator moves eastward. It's just the way it is. That's the way the Earth turns. And so the ship is moving eastward too fast, the ground isn't keeping up. But if you make the orbit bigger, it takes longer. First of all, it's more distance to travel, and Earth's gravity gets weaker out there in those big orbits. And so the bending effect is more gentle. And so you can go slower. And there is a correct distance, and I should know it but don't remember it, where the orbit takes 24 hours. In that case, if you do it eastward over the equator, the Earth turns under, and the two go together. And so if you're on that spacecraft out there and you look down, you go, oh, look, it's Ecuador. And you keep going, oh, Ecuador kept up with me. Oh, Ecuador. It's the only place I know that's right on the equator, right? So it works its way all the way around, and the satellite appears to hover because the Earth is turning right along with it. And so a lot of satellites that you use for telecommunication, where you know the satellite's there all the time, like DirecTV or Sirius XM radio, or those geostationary satellites. They're hovering. They're over the equator. You know where to look them. They're not going over the poles. They're going over the equator, turning with the Earth. And it's always in the same spot in the sky. And you can aim your satellite dish at it and get it all day. Is that okay? Other questions? So all these orbits, they all involve very high speed. And because if you don't have that horizontal speed, you're going to come back down. And that means that all these space launches that are not just let's go visit space for 30 seconds or a minute, or I don't know, maybe it's 10 minutes. The ones that actually want to stay up there for some length of time, they all have to get a lot of horizontal component to their velocities. And they do this at great expense of fuel and energy. They're heroic efforts to get up to that kind of crazy speed sideways. But if you watch the launches start vertically, but they very quickly shift over towards horizontal. They want to gain altitude. In part, that gets them out of the air and gets rid of air resistance. But they also want to start gaining horizontal speed because their goal is pushing 20,000 miles per hour sideways. And they do that. And the direction that they head matters too. If they go eastward, life is easier for them because they start on a surface. They go eastward and they start from near the equator. They start already with 1,000 miles per hour toward the east. That's how fast Ecuador is heading east, about 1,000 miles an hour. That's a good advantage. You might as well start with that. You don't want to go west. It's hard work. And you don't want to launch from high latitude like the North Pole where it's basically stationary. It's just a disadvantage. So if so for public service announcement sort of thing as opposed to tools for living. If you watch some of these companies vying for where to launch and how to launch, they play tricks. I mean, they're physics tricks. They launch from latitudes close to the equator because they get that advantage of the moving Earth to get them up to speed. What else? Launching from high altitude helps too. It gets you through the early air problem. So some of the launches take place from airplanes. They fly the rocket up to 30,000 feet or 50,000 feet, get it out of most of the Earth's atmosphere to begin with. They head east really fast, and then they launch the rocket. And the fact that there's no launch pad, who cares? The launch pad's irrelevant. It's just the act of throwing the fuel backwards. And so some of the launches are from high altitude air. Anything else? Any questions you all have? I did everything. Last tidbits about the moving from planet to planet or planet to moon and stuff. They go into orbit, they stay in the orbit for a while, and if the orbit's circular, they're traveling just the right speed that they're neither going to higher altitude nor lower altitude. All works out, they loop. If they speed up, they've got too much inertia, they go to higher altitude. And if they speed up gently, they go to higher altitude, and they form, again, a closed loop. It's now elliptical rather than being circular. If they go to still higher speed, the loop fails to close. It becomes an arc that never closes. It's either a parabola or a hyperbola. These are mathematical curves, but you can make it so that parabola or hyperbola leaves the Earth and goes towards the moon. So that's what they're doing in going to the moon. They speed up. They pick up enough speed that they start to arc to higher altitude and head off into space toward the moon. And when you get to the moon, they slow down, so they go from what would be an arc around the moon to being a loop around the moon. And so in your lifetimes, you'll probably see space travel back to at least the moon and maybe to Mars. Think twice before you sign up to be the passenger to Mars. Otherwise, see you later. Anyway, it'll be part of your future experiences. All right, well, have a good break and see you next Friday. Remember, long break.